Stanford University.
Today what we're going to do, oh, you had homework, right? You had homework to build a black hole and bring it in, right? Did you build one? Show and tell? No, okay. All right.
Well, I tried that, and I, of course, cheated by going to Mr. Google, who pointed me to Wolfram website, which has the calculation.
Calculation of what?
The radius of a black hole that had the mass of, or had the temperature of 3 degrees.
Oh. Okay.
The difference was that they put Boltzmann's constant in the denominator.
Yeah, it doesn't matter. Suppose you didn't know the answer. Let's try to estimate it. Did we do this last time? All right. We want a black hole whose temperature is in 3 degrees. Why 3 degrees? Well, 3 degrees is the temperature of empty space due to the cosmic background radiation. So if we had a black hole, which was 3 degrees, it would be in equilibrium with its surroundings. Now, would that be particularly interesting? No, because if it got a little bit hotter by accident, then it would just proceed to get yet hotter. If it got a little bit cooler by accident, by emitting too many photons, it would suddenly get cooler. So there's no real equilibrium. But nevertheless, just to try out some numbers, a 3-degree black hole, 3 degrees Kelvin black hole. All right, does anybody know the wavelength of light, which is about 3 degrees? If you know it, tell me. Otherwise, I will have to work it out. It's about a centimeter?
No, it's bigger, it's longer. Isn't it near, it's not 21 centimeters.
No, it's not 21 centimeters.
I thought it was something longer.
It's microwave.
Yeah, it's microwave. Microwave background. Okay, so what is it if it's a... Oh, no, it's not 10 meters. No. 10 meters, no.
Microwave is usually from 1 millimeter to, 1 centimeter.
Yeah.
But it's certainly on the order of a few, it's in the order of centimeters.
Yeah, it's in the order of centimeters. So let's just say a centimeter, okay? Let's say... What? Yeah, it's got to fit in a microwave oven, that's right. That's right. Good point. So it's got to be less than a foot. Less than a bread box. Yeah, but it's order a centimeter or so. Okay, now, here's a fact, if you haven't noticed it already, that the wavelength of light at the temperature of the black hole is about the same size as the radius of the black hole. There aren't too many parameters around that you can shuffle around, and the wavelength of light emitted by a black hole of size r, that wavelength is about r. So we can read off from that what the radius of a black hole which emits 1 centimeter light is, and the answer is a centimeter. So we now know its Schwarzschild radius. Now, what was the question again? How big was it or how massive? How massive? Okay, so let's go with how massive. If it's 1 centimeter, how many centimeters are there in a kilometer? 1,000 times 100, 100,000, right? So there's 10 to the 5 centimeters in a kilometer, and a solar mass black hole is about a kilometer big. I don't know, maybe it's 2 kilometers, maybe it's a little bit bigger, but it's a few kilometers big. So the thing we're thinking about is 100,000 times smaller in radius. How about in mass? the mass and the radius are proportional to each other, 2 mg. So it's 100,000 times lighter than the sun. About how massive is 100,000 times lighter than the sun? It's about the Earth. It's roughly order of magnitude the Earth, the mass of the Earth. So if the mass of the Earth were compressed to a black hole, it would be roughly a centimeter. So that's. But why did that come up? I can't remember now. Somebody asked about it. Or somebody, yeah. Does that agree with what Wolfram says?
I put the numbers in and got about a moon mass.
Moon mass. Sounds a little small to me. Moon sounds a little bit small, but the point is it's not a thing that you're going to hold in your pocket. Right, okay. It's pretty heavy. I'm surprised it's moon mass. I would have thought lighter, but okay, well, that's not important. Factor of what? No. The moon is about a quarter of the radius of the Earth.
But the gravity on the moon is 1/6 of that.
That doesn't. No. Okay, let's not get into it. Let's not get into it. We want to build ourselves a black hole now. We have some moving parts or some working parts, and let me remind you what the working parts are. The first two working parts are the Penrose diagrams for flat space and for a Schwarzschild black hole. So let's draw them. We don't want to do any real calculation. Calculation is too hard. We want to draw pictures and get the basic mathematical facts from the pictures. All right, so let's start with flat space. First of all, over here, just to remind you what a Penrose diagram looks like, I'll draw a flat space over here. There's time. Now, the other coordinate in the problem is not going to be x, it's going to be radial distance. So it never goes negative. Radius is never negative. Radius goes this way. I seem to have made it a little bit negative over here. It goes that way. And at every point at T and R, there are also the angular directions. So here are my coordinates. My coordinates are polar coordinates centered at me. I'm right over here. I also have a clock, so I'm moving vertically. My clock is ticking off time. And at different distances from me, that corresponds to different R, but at every R, there's a sphere of points. So an object could be at any point on that sphere, but we're going to suppress that sphere. We're not going to draw it. We're just going to draw R and T. Light rays that move toward the origin come in along 45-degree axis. Light rays that move out from the origin go out at 45 degrees, and so forth. All right, the Penrose diagram that goes with this is just gotten by smushing it. Smushing is a mathematical operation. And look it up in Wolfram. Look, Wolfram smushing. All right, we smush it this way and that way until we get it on a finite plane. And when we do so, and there's more than one way to do it, incidentally, but they all look the same. There's more than one functional form that you can use for the coordinate transformations, but they all look very much the same. The point over here, that's sort of the origin of both space and time. There's nothing special about this point versus this point versus this point. They're just a different time. But let's pick a origin of time and put it right over here. This is time equals infinity, and it corresponds to the location, the scrunched location of all the people at different radii who just stand still. If they just stand still, they just wind up vertically up at t equals infinity. But on this figure, they all wind up at what looks like a point, but of course that point is not a point, it's just the fact that we've squished everything. Smushed, squished. These are all the, and they get denser and denser as you go out here, because after all, there is an infinite distance out to infinity, and that's all being plotted on this Penrose diagram. So the vertical lines, which become kind of hyperbolas, not necessarily exactly hyperbolas, but looking hyperbolic-ish, they accumulate, meaning to say they get closer and closer over here and here, and that's the vertical lines. The horizontal lines, which are the lines of constant time, well, the one at t equals 0, that's pretty obvious. It starts here, and it goes out to infinity. The one at t equals 1 also goes out to infinity. It looks like that. These are not necessarily, in fact, they're not straight lines as a rule. And again, they get closer and closer and closer and closer as you get up toward the infinite time. Same thing in the lower part of the diagram, which I won't draw. Right. If you've drawn it correctly, then light rays move on 45-degree lines. As I said, that's partly just definition of the way you draw it. And as somebody pointed out last time, had I drawn it accurately, a light ray would then move, well, apparently I didn't draw it very accurately, because it's going to wind up over here. Maybe I can just put another one in. That's better. And so forth. That's a light ray from the origin out. A light ray from out back to the origin is that way. You can have light rays that started later and hit the origin later and then go back out. That's fine. They're all pretty much the same, except one is later than the other. You can also imagine light rays which don't hit the origin. So again, I'm the origin. You flash your laser at me, and it goes by me at a meter. From the point of view of radial distance, it comes in from a long distance away, and it sure looks like it's aimed toward me. So it's hard to tell that it isn't a radial light wave. But then as it gets closer, instead of getting into r equals 0, it gets a certain minimum distance in and then goes back out. So a light ray that misses the origin, here's another one that misses the origin. I'll draw this one bold and bold. Comes in, pretty much the same, and then goes back out. I didn't draw it with any great accuracy, but you get the idea. They all look the same, incidentally, far away. Every light ray, no matter how much it misses me by, if it's far enough away, it looks like it's aimed toward me. Okay, that's flat space. That's that's one of the moving parts, or one of the Tinker Toy elements that we'll put together to build our black hole. And when I say build a black hole now, I mean, at least mathematically or in imagination, create a black hole, as opposed to just take the mathematical structure and examine it. How would you go about creating one in the laboratory? Well, we need a pretty big laboratory, but all right, the next thing was the Penrose diagram for the Schwarzschild black hole. I drew it for you last time, and I'll redraw it now. It is a little bit odd. Here's the way you draw it. You begin by drawing a square, but on the diagonal. You know, a diamond, a square diamond, like that. Then you draw another square diamond next to it of the same size. And then from the top of this diamond, you draw a wiggly line to the top of this diamond, and from the bottom of this diamond, you draw a wiggly line to the bottom of that diamond. The wiggly lines are the singularity, future singularity. Let's call it singularity plus, singularity minus. People outside the black hole, they're over here. This side, we're going to find out, doesn't really mean anything. So don't obsess about this side. Don't even ask me about it for the moment. We're going to find out what happens to it. Here and here are somewhat unphysical. But this region over here, far away from the black hole, it ought to look like flat space. If the black hole were 1,000,000 miles away and we're far away from it, it ought to look like good old flat space. So it ought to look like what flat space looks like out beyond a certain distance here. Well, that's not too hard to imagine. Here's r equals infinity. That matches this point over here. Here's t equals infinity. Here's t equals minus infinity. Light rays come in from here. Light rays go out here. Lines of constant r, and that can mean either Schwarzschild r or rho, it doesn't matter. Proper distance, here is r equals 2mg right here. If you come in along a line like that, you get to r equals 2mg right over there. Let me draw that line a different color. This is the line t equals 0. And t equals 0 starts far away and comes into the horizon, right at r equals 2mg. So that's r equals 2mg. Here's a later time. Here's a later time, and so forth. Earlier time, earlier time. Now this is r equals 2mg. How about r equals 3mg? In other words, farther out from the horizon, that's going to look something like this. R equals, I don't know, 6mg. I'm not sure exactly where it would be, but on this diagram, there's r equals 6mg. R equals 100 mg, far from the black hole. That's out here, and so forth and so on. So, as you can see, this figure and this figure look pretty similar as long as you're far away from the black hole. But this figure looks quite different than this one does near r equals 0. Here's r equals 0. Light rays bounce off it. There's no r equals 0 that light rays bounce off here. Instead, a light ray will just move right through the horizon and hit the singularity. Okay. So near the black hole, they're different. Far from the black hole, they're similar. Once you're in here, as we've talked about before, you cannot escape. You're doomed. You'll hit the singularity. Okay. Now, one more ingredient that goes in is a theorem. I called it Birkhoff's theorem. It is called Birkhoff's theorem. And Birkhoff's theorem is a generalization of Newton's theorem. So let me remind you about Newton's theorem now. Because we're going to put these elements together in a minute. Newton's theorem, let me first express it in a general way. If you have a spherically symmetric distribution of mass, in other words, it's isotropic, the same in every direction. Here it is. It doesn't have to be a shell. It could be a lump. It could be a shell. It could be a solid sphere with uniform density, like the Earth. Well, the Earth is not quite uniform density. Or it could be a sphere like Jupiter with varying density, more dense in the center till you get out to the outer boundary where it has almost no density. It doesn't even have to come to an end. It's just a spherically symmetric distribution. Then what Newton's theorem says, and the analog we'll discuss in a moment, what Newton's theorem says is if you take any sphere, that the gravitational force of a test mass of a point at that distance on that sphere is exactly the same as the gravitational field of the same amount of mass, not the total amount of mass, but the mass contained within that sphere as if it were located right at the center. So the force on this particle here is as if the entire mass inside the sphere were concentrated at the center. And the mass outside the sphere has no effect on the gravitational force on that particle at all. That's Newton's theorem. Okay. The special case of it, which I'll be interested in, oh, and yeah, all right, so what about, let's go slowly. Supposing the mass distribution terminates at some radius so that out beyond that radius there is no mass, then the theorem says that if you're out beyond that mass, the entire massive object gravitates, as far as you're concerned, exactly as if the entire mass were at the center. Now let's take the case of a shell. Let's apply that to a shell. Let's apply that to a shell. Now the blue line is a shell of mass, the blue circle, or the blue sphere, if I want to be accurate, is a symmetric shell of mass. If we wanted to think really mathematically, with too much precision, no doubt, we would imagine that it was an infinitely thin shell, but we don't have to do that. All right, it has a certain mass m, and the gravitational field of a particle on the inside, well, how do we find it? We take that point, we put it on a sphere, and we say that the gravitational force on that point is exactly the same as the gravitational force of all the mass inside the sphere. But there is no mass inside the sphere. So the gravitational field or gravitational force on something inside the sphere is 0. The interior of the sphere is exactly the same as if there had been no shell of mass there at all. And what about outside the sphere? Outside the sphere, it behaves exactly as if the same amount of mass was concentrated at the center. Okay, now let's take Birkhoff's version of this theorem. B-I-R-K-O-F-F? K-H-O-F-F, Birkhoff. Birkhoff's theorem says a very similar thing. It says, we'll take the case of a shell of mass, but it doesn't really have to be a shell. You can say very similar things for any mass distribution. But for the special case of a shell, it says that the metric tensor is the gravitational field, or better yet, the geometry, the space-time geometry inside the shell is exactly the same as if nothing was there. In other words, it's just good old flat space-time, Minkowski space-time, the simplest thing with no curvature, no black hole, just empty flat space. And outside the shell of mass m, the metric is exactly the same as if there were a black hole near the center here of mass m. So if it's a big shell, let's take, for example, the mass of the Earth. I'm not going to make a black hole out of it. Just take the mass of the black hole, the mass of the Earth, and leave it as the mass of the Earth. The only thing I'm going to do with it is smooth it out so that it's perfectly symmetric sphere. Then it says that if you're outside the surface of the Earth, the geometry is exactly the same as the Schwarzschild metric corresponding to exactly the same mass. In other words, it behaves exactly the same way, or the gravitational field that you would feel, would be the same as that little 1 centimeter nugget that formed the black hole of the same mass. Okay, so that's Birkhoff's theorem. Now we want to put together, we're going to create ourselves a black hole, and this is the simplest of all ways to create a black hole. It's the simplest of all ways to create a black hole. What do you imagine? You could try to do this at Livermore, but I don't think it would work. Livermore, you know, they have these lasers that and they shoot them off all simultaneously, and radiation, a shell of radiation comes in, and hits something and squeezes it. I have no idea whether it'll ever work or not. I really don't know to do what they want to do. But if you imagined a much more symmetric field of lasers here, where you really fill this thing up and made it a very, very smooth shell of lasers, and then did your flash thing with the lasers, it would create a shell of light coming in. All right, so we would begin then, let's undraw the lasers and only draw the sphere of light coming in. So a sphere of light is coming in with the velocity c. It's propagating in with a velocity c. Light has energy. How much energy does this light wave have? Whatever it has. Let's call it E. In fact, from the outside, we would say it has mass. E equals mc squared. So whatever the energy of it is, divide it by c squared, and that's the mass of this object as seen from, let's say, far away. Let's not distinguish energy and mass. E equals m. All right, so this object now is a collapsing shell of mass, collapsing with the speed of light, and Birkhoff's theorem, or Newton's theorem, Birkhoff's theorem, applies to it. What does it say? It says, oh, incidentally, what I should have told you when we were talking about Newton's theorem and Birkhoff's theorem, it doesn't matter whether the mass is moving. As long as it stays spherically symmetric, the theorem is still correct. So here the mass is moving inward, and what we can say is on the interior of the shell at any given time, of course, what may have been the interior of the shell at 1 o'clock may be the exterior of the shell at 2 o'clock, but take the interior of the shell at any time, the interior of the shell at any time, the geometry, the metric, the gravitational field is just empty space, as if nothing was there. On the outside, what do you have? The Schwarzschild metric, the good old black hole metric. So you're piecing them together. We're imagining taking a region of space with nothing in it and sewing it together with a region of space on the outside, and the seam, the place where they're sewed together, is the mass distribution. Let's try to draw a Penrose diagram for that. Let's start with empty flat space. Let's begin our drawing with empty flat space. We don't need this. Ooh. Empty flat space. And into that empty flat space, we're going to throw a shell of light. So we begin by drawing empty flat space. Here it is over here. It's just I'm going to get rid of some of the lines. We don't need all those lines on it. So here's our empty flat universe. Just a triangle. Now, from far away, we're going to throw in this shell of light. Instead of throwing it in from Livermore, let's throw it in from infinity. So the light comes in from very, very far away along a thin shell. And what does that look like? That looks something like this. The red line here is going to be the trajectory of the light ray, or the light shell. Remember, each point in the diagram is really a two-dimensional sphere. So every point on this diagram represents a two-dimensional surface, and every point along the light ray here really represents a shell of light. Okay. So at this point, the shell is very big, it's far away, and it's moving toward smaller and smaller r, and when it gets to the center, the shell has shrunk to a point. That's a lot of energy that we've put into a small volume. Whatever the energy is, if we squeeze it into a nothing volume, we've created a huge energy density. We've created a lot of energy within a small volume. You might think we make a black hole. Okay, and you'd be right. Okay, let's begin. Let's take the first half of Birkhoff's theorem. It says inside the shell, space-time is perfectly flat. Where is inside the shell? Let's imagine drawing one of these surfaces. Along the surfaces, the radius is increasing. Where is the inside of the shell? This is not the inside of the shell. That's the outside of the shell, right? Here's the inside of the shell, from here to here. All right. Let me draw all the places which correspond to the interior of the shell. That's all of this. All of that is the interior of the shell. The interior of the shell, Birkhoff tells us, is just flat space-time. This diagram here was all flat space-time. It means I got the picture right inside the shell. Just by drawing flat space-time inside the shell, I got it right. Outside the shell, I don't have it right. What does Birkhoff's theorem tell me outside the shell? It says outside the shell here, the metric should be the metric of the black hole. So let's draw the black hole metric. Let's draw the black hole metric. Well, here it is again, but I'm going to simplify it. Now again, so we're throwing in a light ray from infinity. It starts out here, and it comes in, and boom, hits the singularity. Where now is inside the shell and where is outside the shell? Inside the shell is to the lower left. Outside the shell is to the upper right. So where did I get the metric right on this diagram? Outside. Right? Out here. That's what it should look like outside the shell. And this, that's wrong. Also, this is wrong. So let's erase it. This part was wrong. Birkhoff tells us that's the wrong thing for here. And this part is wrong. Notice that among other things, I'm throwing away all this problematic region with another universe on the left, a white hole in the singularity in the past, and I'm left with only this. That's the portion of the black hole metric outside of the black hole. So here's the light ray, and it intersects, it hits the singularity right over here. Here's the light ray, it comes in and gets to r equals 0 right over there. These 2 points must be the same point, the end of the light ray trajectory. All right? Now what I want to do is I want to imagine taking this and simply pasting it on top of this. Pasting the two together, and here's what it looks like. Out here, that's the Schwarzschild metric. I've erased the rest of it, but here it is. It's everything above this red line. That's what goes here. Everything below the red line, that's here. That's the simplest formation of a black hole. And the reason that I spent some time at it was to show you, among other things, what happens to these crazy regions, the other half of the wormhole, beyond the wormhole, and what happened to the white hole. White hole's not there. The wormhole's not there, but there is a singularity there. The singularity is there, okay? Okay, having established any questions up till now?
Seems like one of the distances is the horizon and the other is...
Well, so far we haven't even talked about the true horizon of this geometry yet. We're going to do that in a minute, but go ahead, ask the question anyway.
Asking about that point where you paste them together on the upper left, or maybe not Right.
Yeah.
On the interior space one, we had an R equals 0. But in
That was right over here.
yeah, but in the exterior one, we had only the horizon, right?
No, no. At the singularity, r is equal to 0. Right? Good. That is, all right, that's a worthwhile point now. If you remember, if you go back to the Schwarzschild metric, the singularity was exactly where that little two-sphere shrunk to 0, where r went to 0. Okay? So in fact, you're matching r equals 0 along here with r equals 0 along here. And they do match. That's the construction of a black hole. That's the way you would do it. This is the kind of black hole you would get. So let's now ask, where is the horizon? Where is the horizon of this black hole? The definition of the horizon now is not r equals 2mg. That was a temporary definition of the horizon. The horizon is the surface which separates the region. Let me say this clearly. There are those places where it's possible to send a message out to infinity. In other words, to send a light ray out to infinity. If you have enough fuel in your engine, you have a chance of escaping from those regions. But in particular, light rays can escape from certain regions, and from other regions they cannot escape. The definition of the horizon is the surface which separates those two regions, period. It's the surface in space and time which separates those two regions. That from which you can escape the singularity and from that which you can't. Well, it's very easy to see where that is. You just draw a light cone back to here. If you're over here, can you get out? No. You'll wind up at best over here. What about if you're out here? Can you get out? Sure, you can send a light ray out. Anywheres to the lower right of the green line, a light ray can get out. Now, a light ray can also get in. You can also throw a light ray in. That's just to say, from the outside, you can throw things into the black hole. You cannot, from the inside, throw things out of the black hole. So the green line here is the separator that separates the places where you can escape from those where you can't escape. Now notice something curious. Below the red line here, it's just empty flat space. There was nothing there. It was just good old empty black space, flat space. The signal of the incoming light shell hadn't even gotten there yet, and yet there is a horizon there. What's going on? Well, just think about somebody who happens to be over here. He doesn't know anything at all about this light shell which is going to come in. The light shell, he receives no message that this light shell is coming in. The light shell originated over here. A signal cannot get to him, knows nothing about it. The light shell is coming in, but he doesn't know it, has no knowledge of it at all. Nevertheless, the fact that that light shell is coming in means he's trapped. He cannot escape to infinity. That light shell is going to get him. You can see why. I don't have to, words, a picture is worth 1,000 words here. He's behind this line. He cannot get out of that line without exceeding the speed of light. And so he's going to hit the singularity. Even though nothing has happened there yet. The geometry is flat space, and yet the horizon is over here. The horizon forms before the light shell gets there. Does anything really happen there? Can anybody see anything? Somebody moving over here, do they see something happening? No. Nothing special happens over there. But whether they like it or not, they're doomed by the time they get past that light shell. I'll give you an example. I've used the example many times of a drain hole as a black hole. The drain hole, a lake, a big, big lake, with a drain hole in the center where the water is being sucked out so fast that at some distance away, the drain hole is draining away water so fast that a rower who is trying to outrow the current can't outrow it because the velocity inward is too fast. Okay, so now imagine that the drain hole is shut off. You've plugged up the drain hole. You're sitting a couple of meters away from where the drain hole is. Nothing is happening. The water isn't moving. You're perfectly happy. If it stayed like that forever, you would have no trouble rowing away. But now, unbeknownst to you, somebody pulls the plug from underneath, and all of a sudden, the water starts rushing toward the center. You are doomed, whether or not you felt anything going on. You're doomed because all of a sudden, the velocity of the water is such that you can't outrow it. So there's an example of you're past the point of no return, even though there's no flow of the water at that point. Same is true here. Pulling the plug is analogous to this light sheet coming in. Once the light sheet, the light sheet comes in, anybody who happens to be in here is trapped. What happens to the horizon? Let's think about the horizon a little further. Here's the horizon, and remember, at each point on this diagram, there is a two-dimensional sphere. So each point along here represents a two-dimensional sphere. What's the size of the sphere over here? 0. All right? So we start over here with a 0-size sphere. There it is. Now we move out a little bit along the horizon. How big is the horizon over here? Well, it's slightly bigger. The horizon has grown, even though nothing's happened. Nothing has been going on in here. And the horizon keeps growing up until this point here, when, how big is it at this point? 2 mg. 2 mg, where the mass, remember, we've just taken a black hole geometry and sort of welded it on over here. And the black hole geometry on this side had a horizon whose size was 2 mg. So it just grows until it becomes of size 2 mg. And then it just stays that way, unless somebody throws in some more stuff. If somebody throws in some more stuff, the horizon will grow. Okay? So that's a picture of the creation of a black hole from an incoming light. Yeah.
So you're saying the reason that the plug gets pulled out of the drain is because of the sphere's light getting smaller and smaller? Concentrated.
Right. But I only use that example to show you that even though nothing has happened yet, you could nevertheless be beyond the point of no return. Or you could be like on the edge of Niagara Falls at a time when Niagara Falls was so frozen up that it wasn't moving at all, and you think you're perfectly safe, there is no point of no return, the water's not moving, and then all of a sudden the ice gives way and the water starts going, you're doomed. It doesn't matter that nothing seemed to be happening. Same kind of thing. Okay, shall we take a break?
Regarding the fellow that gets trapped in there not knowing it's coming,
Over here.
right here. And an earlier class we said that all the mass of the lower did say this, but I'm wondering if he gets seen to, is he on the outside of the horizon from a point of view of a distant observer? Everything that falls on.
No, the distant observer can't see him. The distant observer's out here, can't see him.
So does he go right into the center? So what is the status of something that's inside?
Here, there he is.
Right.
What can happen to him? He can hit the singularity. He can't avoid it. Right.
So anything that's trapped into the
Yep.
forming horizon goes to the singularity, and stuff that falls in subsequently appears to be stuck on the horizon forever somehow.
Well, okay, so he got in here somehow, didn't he? I mean, well, he was trapped, but he didn't begin existence over here. He may have come from here, huh? His particles. His particles. Maybe his mother was over here, and his grandfather was over here, and so forth and so on. Or maybe he just accidentally collected, came to existence as a funny fluctuation of a bunch of molecules, but those molecules were there before, atoms or something was there. The energy was there beforehand. So the energy came in here, and there he is. And yes, somebody looking back can see his grandfather, or his father, or whoever it is, or his particles, but can't see him. In fact, what he sees is he sees these particles just collecting on this horizon, which is peculiar because in some sense the black hole hasn't even formed yet. Hey, look at that, this is weird. No, this is really weird. The observer up here looks back and he sees grandfather falling in, and then there he is. He's born over here. He looks back, and what does he see? He sees grandfather getting closer and closer and closer to something which doesn't exist yet, but never sees him go past it.
Oh, no, it goes through that point very close to the horizon, intersect at the rest. So, I mean,
What?
it's a space-time diagram. It goes through the
We're asking what somebody on the outside sees. We're asking, or measures.
No, but that sight line, looking back at where that photon has come from, it
Yes.
goes through the red line.
It goes through the red line, yes.
So it's actually close to where it formed.
The person out here knows that a black hole formed. He knows a black hole formed. He sees the light coming from. He has no problem knowing that a black hole formed. He can look back and he can see the shell coming in. So the person out here knows that the black hole is formed. The odd thing is that he sees this person over here getting trapped onto the horizon even before the shell got in. Looks back, looks through the shell. It's just light, he can see through light. He looks back through the shell and sees,
So that continues the idea that everything from an outside observer will see, any mass that's in there, will be somehow smushed onto that horizon.
right,
Always.
right. Forever and ever and ever, or until the black hole evaporates. Right. All right, now we're going to come to the really bizarre questions that have to do with the combination of black holes, gravity, and quantum mechanics, and information, and all that kind of thing. Let's draw a picture of the horizon now as a different picture. The horizon is just a surface. Here it is. We're going to fall downward now. Here's the horizon. It's really a great big sphere. But just like the surface of the Earth is a big sphere, let's take the flat Earth approximation, or the flat horizon approximation, and just think of the horizon being over here. Things fall down in this direction toward the horizon. And let's talk about the properties of the region near the horizon and what happens to things as they fall to the horizon, through the horizon, whatever. Let's talk about what happens to them. Now, one of the things we discovered earlier on was that black holes have temperature. Black holes have temperature. We even discussed the temperature. I think we even or roughly calculated it. They have entropy. The entropy is proportional to the horizon area. So it's almost as though the entropy was carried by things which were sort of wallpapered onto the horizon. Maybe not so surprising, since from outside, everything that fell in does look like it's sort of plastered onto the horizon. So maybe it's not all that surprising that the entropy of the black hole is proportional to the area. We discovered that if we tried to throw in more bits, it made the black hole bigger. Every bit increased the area by 1 Planck unit, the area of the horizon. And we went through that. That's a quantum phenomenon. Involves h-bar. So there was entropy, and there was also temperature. Anybody remember what the temperature, the Hawking temperature of a black hole is? Let's get rid of some of these pictures over here and go back to Hawking temperature of a black hole. Let's call it TH. Do you remember what it was? You're going to look in your notes. You're going to cheat.
H bar C cubed over H pi mg.
H bar, is it C cubed? I think it's C cubed. C cubed over 8 pi mg, which we could also write in terms of the Schwarzschild radius. 2mg divided by c squared is the Schwarzschild radius, so this is also equal, I think, to hc over, looks to me like 4 pi r. Do I have that right? Two mg, I'm slow, I have to put a 2 here and then divide by 2. Yeah. But in particular, in units in which h bar and c are equal to 1, which are natural units for us, the temperature of the black hole is proportional to 1 over the radius of the horizon. And the radius of the horizon of a big black hole is big. And so black holes are cold. They're cold. Now, what exactly does this temperature mean? Can temperature depend on position? In some sense, yes, and in some sense, no. What is the sense in which the temperature can depend on the position? I can tell you right now, the temperature in New York City is not the same as the temperature here. Okay. But you said the temperature can't depend on position, right? That somebody says not. Explain yourself.
In empty space, it doesn't matter where you are, the temperature's the same.
That's true in empty space. In truly empty space, the temperature is 0. In thermal equilibrium, temperature is really only accurately defined with infinite precision in equilibrium. Temperature is a thing that has to do with thermal equilibrium. Thermal equilibrium is what happens when everything gets equilibrated. In other words, when all the variations in temperature, when the heat flows in such a way as to increase the entropy to the maximum amount, and then temperature in thermal equilibrium is exactly constant. Now, this is a true statement, but one has to understand in a gravitational field exactly what it means. It does not mean, here's a gravitational field. It does not mean in thermal equilibrium, it does not mean that if you took an ordinary standard thermometer and lowered it down or raised it up, that the temperature would be the same. Here's why. Temperature, what does temperature measure? Roughly speaking, very roughly speaking, it measures the kinetic energy of particles, right? All right. Now, supposing we had that the surface of the Earth was being heated from underneath. Here's some flames. These are green flames heating the surface of the Earth from underneath. making the surface of the Earth hot, and it was ejecting thermal molecules into the atmosphere. In fact, those molecules were the atmosphere. Let's go to an extreme situation where the molecules are so rare that they don't bang into each other. The mean free path between them is very large, or the molecules are so weakly interacting that basically what happens when a molecule gets ejected is it falls back down. So this, above the surface of the Earth, there are molecules, gravitation is pulling them back down. They jump up depending on their kinetic energy. In other words, they jump up by an amount which depends on the thermal fluctuations that they might have gotten hit with. The hot surface here is bombarded, is vibrating, shaking, doing whatever hot is fluctuating, and it'll kick a molecule up, and the molecule will fall back down. Okay? Do you expect the kinetic energy of the molecules to be the same no matter how high you are? No. Why not? Because they lose kinetic energy when they rise up. Right? Supposing you wanted to know, so here's an example where even though in some very technical sense, which I'm not going to try to describe for you exactly, the temperature is the same everywhere. There is a sense in which that is true. But for our practical purposes, where what we mean by temperature is that which is measured by a thermometer. And what is measured by a thermometer? The kinetic energy of the particles that are hitting the thermometer. The temperature would be higher down low than it would be up high. Okay? So, or the kinetic energy of the particles would be higher down low. The same would be true, incidentally, if these were not molecules, but we were radiating photons. Photons would also get radiated, and photons are also subject to gravitational forces. Photons which are radiated will also fall back down. In fact, as they rise, they lose energy. As they fall, they gain energy. So it's the same with photons. Photons are no different. All right, now let's suppose you were very, very far away. You didn't want to get too close to this thing, but you wanted to know what the temperature was down below. What would you do? Well, you'd measure the temperature high up, and you say, well, it's half a degree temperature high up here, but you could extrapolate down and say if the typical kinetic energy of a particle or a photon that you see up 100 miles from the surface is such and such, then you could just use some straightforward extrapolation and figure out what the temperature is down near the horizon, or near the surface of the Earth in this case. Right. Now, what is the Hawking temperature? The Hawking temperature is the temperature seen by a thermometer far from the black hole. It's the actual temperature that a thermometer would register if it were very far from the black hole. It would be registering the presence of photons, thermal photons, black body thermal photons, which somehow were ejected from the black hole and which were out there as a kind of atmosphere far from the black hole, which were exciting the thermometer far away. And the temperature is pretty cold. But in the same way, you can extrapolate downward and ask what the temperature must have been close to the surface of the black hole. There actually is a formula for doing it. I think it's a little bit too late now. Maybe we can go through it another time. How you actually calculate the variation of the actual measured temperature in a gravitational field. But I'm going to tell you the answer. The answer, first of all, is that very far away, the temperature is the Hawking temperature. Where is it? Here it is right over here. As you get closer and closer to the black hole, the temperature rises. And as you get very close to the black hole, as you get close to the horizon, we won't call this the Hawking temperature. It's kind of the extrapolated Hawking temperature, what you would extrapolate into. Let's give it a name, T of rho. It's the temperature measured at a proper distance rho from the horizon. It is 1 over 2 pi rho. 1 divided by 2 pi rho. The closer you are, the higher the temperature. Now, in fact, the horizon is a very difficult place to escape from. In fact, if you're behind the horizon, you can't escape at all. If you're right at the horizon or very close to the horizon, it's extremely difficult to get away, which is another way of saying you lose a lot of energy. A photon loses a lot of energy when it tries to escape from very close to the horizon. So if you see a finite temperature a distance above the horizon, then extremely close to the horizon, the kinetic energy must have been very large. That's what's going on here. The actual temperature of the photons or of a thermometer that would be lowered on a cable. Here's our experiment. We're going to lower a thermometer on a cable. It's going to be a tiny, tiny thermometer because for one reason or another we have to use tiny thermometers, but we'll lower a tiny thermometer on a cable. The cable will send back a signal telling us what the temperature recorded on the thermometer is. And as you lower it down, you'll find the temperature goes up. It's up and up and up and up. Well, if you really believed this, then you would say that the temperature close to the horizon was very, very hot. Now, we have a funny situation now. Let's suppose we take an atom and we lower it down closer and closer to the horizon. What happens to that atom as it gets close to the horizon?
Time dilation.
Forget general relativity. Now, it's just moving into a very hot region. What happens to it? It becomes excited. But it's getting hot. It's getting really, really hot. It gets ionized. It's getting really, really hot. The nucleus gets torn to pieces by the high temperature. The quarks get liberated. It's defeated. Yeah, right. Well, yeah. Right. Yeah, that's right. I mean, you know, if we lowered, if we put a cable around you and lowered you down and put your feet to the surface of the black hole, you would get a hot foot. Right. Right. That's what this picture says. And how do you get away from it? You've done a calculation. You've done a legitimate calculation, and this is a legitimate calculation. I mean, the calculation is correct, and by now it's been tested over and over again. If you do lower something down on a cable and then pull it back up, it will give all of the evidence of having been in a very, very hot region. So this is not to be questioned. But there's something a little funny about this, because from this point of view and from this picture over here, the horizon is nothing very special. It's just a green line that I drew there, but there was nothing there. It was just a mathematical line that I drew to separate the region from which you can send a signal out to a signal where you can't send a signal out. But on the other hand, nothing special was going on in this horizon over here. The curvature didn't get large. The metric near the horizon was close to flat space. We've already established that. And so there's nothing very dramatic going on. And so you might expect that if you dropped something through the horizon, and now think about it in the frame of reference of the falling object, the falling object doesn't say it took an infinite amount of time to go through. Here's the falling object going through the horizon. The clock ticks off seconds, It took exactly 7 seconds to go from here to here. In the frame of reference of the falling object, the object says, I fell through, or I fell past the point where I originally calculated there was a horizon. He doesn't say, bump, I just felt the horizon. But when he was outside the black hole, he made a calculation of where the horizon was, estimated how long it would take him to fall through it, fell through it, nothing happened. Okay? So, from the point of view of somebody who falls through the horizon, nothing happens at that point. It sounds contradictory. It sounds, I mean, either he does get burned up or he doesn't get burned up. And if he doesn't get burned up, how did he avoid the consequences of this very, very high temperature? Or it could be an atom. Does the atom get ionized? And if it does get ionized, do its particles get spread over the entire horizon by the extremely high heat, which causes things to diffuse? Or does it fall through here? There's got to be an answer. It's one or the other. It can't be both, right? So I think one way of trying to get at this is to try to think as much as possible in what I would call an Einsteinian kind of way, or maybe it's a Heisenbergian kind of way, to try to be operational about it, to try to say, look, let's see if we can prove or disprove this or that by doing an experiment. Now, here's the kind of experiment that you might try to think about. The temperature of this atom here increases as it falls down. In fact, it gets very hot before it passes through the horizon. It doesn't have to go through the horizon to get good and hot. How hot does it have to get to ionize a hydrogen atom? 13 electron volts, right? How hot is that? That's 3,000 degrees, something like that? Yeah, a few thousand degrees. So at some point it reaches 3,000 degrees, it's outside the horizon. At that point, if all makes sense, then it should get ionized. And that's before it fell through. Therefore, it ought to be able to send the signal back out, or somebody stationed over here ought to be able to send the signal back out and said the atom either did or didn't get ionized. From one point of view, the atom ought to be able to say, nothing's happening to me. I'm falling freely through the horizon. I'm within a certain distance of the horizon. You told me the temperature was going to be 3,000 degrees, but I don't feel a darn thing, and I'm going to send out the message to you and tell you. Right? From the other point of view, you've done a mathematical calculation which says that the temperature gets hot. You've got a conflict, a real conflict. So let's see if we can turn it into an experimental conflict. In fact, before we do, I want to remind you of the Heisenberg uncertainty principle. And the reason is the logic that goes on here and that is important in understanding this better is very close to the logic of that Heisenberg used. What did Heisenberg say? He said you can't measure both the position and velocity of a particle. Okay? In fact, in some sense, it can't have both a position and a velocity. It has one or the other, or you can measure one or the other. If having a certain property means that that property can be measured, then it has one or the other and not both. And that seems contradictory. Why does it seem contradictory? If it makes sense to talk about the position of a particle at any time, then it makes sense to talk about the sequence of positions of the particle. If it makes sense to talk about the sequence of positions of the particle, then it has a trajectory, and that trajectory can be used to extrapolate and find the velocity for the particle. So if it's really true that the particle has a position at every instant, then how can it not have a velocity at every instant? All right, so Heisenberg said, all right, I don't care what you say about whether it does or doesn't. Let's ask if we can really measure both simultaneously. And I just want to very quickly remind you of the logic here. So, all right, supposing you have a particle, an electron, and you want to measure its position to high precision. You want to measure its position to high precision. How do you do it? You hit it with a photon. You create an image of it on a screen. And in order to have the resolving power to see the location of that electron to within a resolution delta x, you have to have a photon. You have to hit it with a photon or a light wave whose wavelength is no larger, is less than or equal to delta x. But then, if the wavelength is less than delta x, that says that the momentum is larger of the photon, is going to be larger or equal to Planck's constant over delta x. Is that the Planck's constant with the cross or without the cross? It doesn't matter. Okay. That means that this particle is going to get bombarded by a photon in order to measure it. You might have said, look, I believe that particle is standing still. I've created that particle in such a way that it's standing absolutely still. And I want to confirm that it's standing. I want to confirm that it's standing absolutely still at the origin. So what I will do is measure its position very quickly, and then instantaneously afterwards measure its velocity and try to check that it was both at the origin and at rest. Well, you know the story. I mean, the story is extremely well known. I'm just reminding you of it, that if you have to hit it with a particle of momentum p, it's going to get hit, it's going to recoil, the particle is going to go off in some direction with a momentum more or less of order p. In what direction? Well, that direction is somewhat random. And so if you try to measure the velocity afterwards, it will not be what you thought it was in the first place. In other words, the experiment creates exactly the condition that it was designed to show wasn't the case. The experiment was designed to show that the velocity was zero, let us say, and just the experiment itself created the condition which was the opposite of what it was designed to confirm. That's the Heisenberg logic. It's deeply, of course, connected with quantum mechanics. H-bar appears in it. In classical electrodynamics, you can make an image with an arbitrarily small amount of, arbitrarily low intensity electromagnetic wave. You don't have to have one whole quantum. In quantum mechanics, you can't subdivide the energy less than a quantum. So if you want to do the experiment, you're stuck. You're going to give that electron a kick. Okay, let's now analyze. Let's be Heisenberg and analyze the question, what happens when an atom falls onto the horizon? Does it or does it not get ionized? Does it or does it not get really mutilated by the high temperatures above a certain line here? Below a certain line. Below a certain line, here's the line rho, at a distance rho, where the temperature T is 1 over 2 pi rho. Now, what we're interested in is when the atom falls below the line where the temperature has exceeded the ionization temperature. We're not interested in what happens when the atom is above the region where it's nice and cold. We're interested in what happens to the atom when it gets within the region where the temperature is of order the ionization temperature. Once it gets down that low, it's in this huge gravitational field. It fell from above. The huge gravitational field near the black hole has accelerated it. And it's accelerated it by that point up to close to the speed of light, in just because just because the gravitational field is so intense near the horizon, so hard to get away, big gravitational field, this thing is falling downward now with close to the speed of light. How much time does it have before it actually falls through the horizon? Once it's through the horizon, you cannot find anything out about it, once it's through the horizon. All right, so how much time does it have to fall that distance? Well, the answer is, what is it, rho over c? If this distance is rho, the time that it has is rho over c, which is proportional to 1 over the temperature, 1 over the ionization temperature. The higher the ionization temperature, the shorter the amount of time that the particle has in that region. Okay, now how are we going to do an experiment from the outside to determine whether before it falls through, it's too late. Once it falls through the horizon, too late. Can't get any information out. We want to find out during this period, this short period of time here, while it's falling in the high temperature region, we want to try to find out if it was ionized. How do we find out if it's ionized? Well, we shine some light on it. Here might be a source of light over here. That light is going to illuminate it, bounce off, and create an image. This image over here is either going to be an atom unionized, or it's going to be an atom splattered all over the place. One or the other, we don't know which. Okay, we have a very short amount of time to do the experiment. Namely, the amount of time that it takes to fall from the region where the temperature first got hot enough to ionize it till it falls through the horizon. That's a short amount of time. That means, what does it mean in terms of resolution power? Another way to say it is we have a small distance that we have to resolve. We have to see that atom within a small distance. That small distance is rho. What does it mean? Well, it means that that photon had better have a wavelength which is smaller than the distance rho. Right? So lambda has to be smaller than rho, and that says that the energy of that photon has to be larger. I'm going to, let's see, h bar over lambda times c divided by c. Let's see, E is P times C. This is P C, right? Or H.
But actually you have a rho over c.
The energy has to be larger than this. The smaller the wavelength, the larger the energy, and lambda is of order rho. So the energy has to be larger than this. Okay. Well, this is essentially exactly the energy that corresponds to this temperature, 1 over rho. We didn't put in the h bars and c's here. 1 over rho. 1 over rho, same thing here. In other words, you have to hit the particle, you have to hit the atom with a photon which is energetic enough to ionize it. In order to see it in that period, you have to hit it with a photon which is energetic enough to ionize it. In other words, you have to create exactly the conditions which the experiment was designed to show do not happen. The experiment will ionize the atom. And there is no way to check whether it was the experiment that ionized the atom. You try to do it again after the experiment and see if it's still ionized. Yes, it'll be still ionized. Any experiment that you do which is designed to prove that the atom wasn't ionized will ionize the atom. And ionize the atom in an uncontrolled way, in a way that you can't go back and check that the atom was not ionized. So, yeah.
Wouldn't that high energy ionize it even in the frame of the falling object? Wouldn't it get hot?
Yes. In the frame of the falling object, yes. Yes, that atom gets whacked. That atom doesn't like what happened. And if somebody out here were to monitor you and see whether you can fall through the horizon or not, if they did an experiment to check They would evaporate you.
But if I'm just falling through,
But if you're falling through and nobody does the experiment, you're fine.
suppose I'm falling through and somebody does do an experiment.
Then then you're in trouble. Then you're in trouble.
Don't do that.
So couldn't you measure far away from the black hole and look for gradients and from that extrapolate?
No, you'd have exactly the same problem. If you try to check that the temperature is rising, what are you going to check? What are you going to check about it? Let's say you just drop a thermometer down. You drop a thermometer, let the thermometer freely fall, and you want to find out if the thermometer has gone up a little bit. How do you find out? You can't ask the thermometer's falling down. You've got to get some radiation back from the thermometer, so you'll have to hit it with some radiation in order to, you have to look at it. You have to look at the thermometer.
Have it record while it's going down.
Well, something has to interact with the thermometer. And what you'll always find, inevitably,
Or you pull it back up after it has recorded its descent.
or then it will show that it was hot. Then it will show that it was hot. Just the acceleration of turning it around will make it hot.
No, but it records the time, so during the free fall period, you only look at that period.
As long as you can be getting information back, that information will be coming back in the form of quanta, and those quanta will either have been emitted by the object or have been interacted with the object. There's no way you can get information without getting quanta back from the object. Either the object radiated those quanta and therefore recoiled, or you hit it with quanta. There's just no way to do it without influencing the object. And the amount of influence is always exactly what the temperature at that point would have done. So it's a sort of catch-22. You cannot do the experiment without causing the thing you were trying to show. Yes, Kevin.
So the high energy of the photon there is to resolve a small distance.
Yeah.
Is that,
Or a small time.
does that end up being the same thing as saying that to get that reflected observation back out of the black hole takes a tremendous amount of energy because you're getting it when it
Strictly, you're not trying to get it out of the black hole. It hasn't fallen into the black hole yet. Yes.
out of the region near the horizon takes a huge amount of energy to get. Does that really end up being the same?
Yeah. 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 It does. It does. In the end of the day, it does. Right. Yeah. That photon did not have to be a high energy photon by the time it got out. Because in traveling out, it will lose some energy. But it did have to be a high energy photon in the region in here. And this atom doesn't care what the photon energy was out here. It wants to know what the energy that was, what it was hit with.
I guess the other way to look at it is if it's going to emit the measurement or the information itself, it has to emit it at such a high energy.
Absolutely.
That region.
Right. Yeah. It doesn't have to be an external photon hitting it. It could be something that it naturally emitted, but that's right.
It seems that the atom falling into the black hole have a preferred direction, namely the horizon. And typically we don't call temperature directed kinetic energy. You throw a baseball, you don't call it hot. You just say it has kinetic energy, right?
Well, it's not the kinetic energy of the object which is falling in. The object is falling in. Its kinetic energy is in temperature, but it's interacting with an environment which is getting hotter and hotter. It's the environment that it's interacting with which is very hot.
The radiation from the black hole.
It's the radiation from the black hole.
Could
Yeah.
you check with a magnetic field if the ion is the ion is ionized?
What's that?
The ionization, can you check with the magnetic field?
If you could, look, you could do an experiment. You could imagine an experiment in a laboratory that's falling with the atom. Could be magnetic fields, whatever's in that. And that experiment, as you fall into the atom, could be doing the experiment. The problem is getting the information back out of the black hole. Right. So whatever happens in that laboratory, you have to interact with the laboratory with something external and then get the information back out. And it will always be the case that the energy of the photons that are necessary to get that information back out are the same, or at least as big as the energy of the environmental photons in the thermal bath.
So if I have a transmitter in the thermometer, by the time I get close to the event horizon, that temperature, the amount of energy I have to generate to send the signal out would evaporate it anyway.
Exactly.
Isn't that distance really very small?
Very small. Very small. No, that's the point. You don't. The distance over which the temperature is high is very small. All right, so you can either think that you have to have a photon of high spatial resolution or high time resolution. Either way, you'll either say the photon has a high momentum or it has a high energy. And yes.
This is all equivalent to the usual Heisenberg uncertainty principle for time and energy, right?
Well, that's what we've used, yes.
Yeah.
Yes, yes, yes. So this puzzle about what goes on at the surface of a black hole, whether it does or doesn't get hot, gets all mixed up with these questions of quantum uncertainties and so forth, and that's the result. There's no way to answer the question other than to do the experiment, and when you do the experiment will do exactly what you were trying to show didn't happen. That's yeah, okay.
Have a high enough resolution to catch it in that window. Is it possible to use a lower resolution, lower energy, and do it a bunch of times and hopefully you'll just catch it right?
Well, you only get one shot at each particle falling through the horizon.
Is the probability just too ridiculous to even?
You say, supposing I did the same experiment over and over with many, many atoms and use a low resolution. I don't know, I never thought about that one. You try to use less energetic photons. Of course, each one, it's a good question. It's a sensible question, and it ought to be answered. Yeah.
We have to have enough energy to get something to come out.
Right.
Same problem you had with trying.
Right, but you don't have to do, yeah.
You have to have enough energy
Yeah.
to pick it out.
Yeah.
There's not going to be any loopholes to go to the uncertainty principle, so.
Yeah. Right. Right. You can't beat the uncertainty principle by what you're trying to do.
Are we saying we can predict that the person falling in won't feel the temperature?
No. We can only say that the experiment will in itself cause the conditions that I was trying to prove didn't happen. That's all we can do from this kind of analysis. In other words, if somebody comes and says, look, I'm convinced that, that somebody who falls through the horizon, nothing happens to them, then my answer will be, yes, can you do an experiment that shows that? And the answer will be no. You cannot do an experiment that shows that. That's all this is designed to show, that at a level of operational experimental physics, it would be impossible to confirm that the atom did not experience a high temperature. And we'll come back. We'll look at a couple of more Gedanken experiments and try to see what they say. Of course, there's no way to say what happens if no experiment is done. You know, it's very much like the two-slit experiment, where if you don't do an experiment, there's no meaning to the question of which slit you went through. So if you don't do an experiment, there's no answer to the question. Yeah. Right. Okay, let's call it a night, and I'll see you next week.
For more, please visit us at stanford.edu.